Two spherical soap bubbles. Two spherical soap bubbles coalesce if V is the consequent change in volume. Consequent change in volume of the contained air and A is the change in total surface area. A is the total change in surface area. Then show that 3PV plus 2A sigma equals 0, where sigma is the surface tension of soap bubble, surface tension of soap solution, and P is the atmospheric pressure. We have two soap bubbles. These are the two soap bubbles having radii R and R. They have the same radius. They coalesce. P1 is the pressure of the first soap bubble and P2 is the pressure of the another soap bubble. V1 and V2 are the volumes of the two soap bubbles. Now they coalesce and form a large soap bubble of radius small r. Two soap bubbles coalesce to form a large soap bubble. This is the large soap bubble. We get a large soap bubble. R is the radius of the large soap bubble. R is the radius of the large soap bubble, and we can denote the pressure and volume of the large soap bubble. Final pressure and volume are P prime and V prime are the pressure and volume of the large soap bubble. Excess pressure PE acts on the concave side of the first soap bubble. Excess pressure acts radially outwards in all the direction, and PE is the excess pressure acting on the concave side of the first soap bubble. Similarly, we can consider excess pressure PE acting inside the second soap bubble, and also you can denote excess pressure acting on the concave side of the large soap bubble. PA, we can denote the atmospheric pressure acting inside the soap bubble, that is PA is atmospheric pressure. Total pressure, the total pressure of the small soap bubble, the total pressure of the small soap bubbles of volume V1 and V2 are given by P1 equal PA plus PE, where PA is the atmospheric pressure and PE is the excess pressure, or comma P1 equal P plus 4S by R1, where R1 is the radius. We can denote the radius of the two soap bubbles as R1 and R2. So we get P1 as equal P plus 4S by R1 and P2 equal P plus 4S by R2. P1 equal P plus 4S by R1 is the total pressure acting on the first soap bubble, and P2 is the total pressure acting on the second soap bubble, where PA equal P, which is the atmospheric pressure. PA equal P, which is the atmospheric pressure, and S and PE equal P is the excess pressure acting on the concave side of the first soap bubble. PE1 is equal 4S by R1, which is the excess pressure, which is the excess pressure, of the small soap bubble of the smaller soap bubble of radius r1 and volume v1, radius r1. Also, PE2 is equal to 4S by R2, which is the excess pressure of acting on the concave side of the smaller soap bubble of radius R2, is the excess pressure of the another smaller soap bubble, of radius R2, where S is the surface tension of the soap solution. When these two soap bubbles coalesce, isothermally and a large soap bubble is formed, a large soap bubble of radius r is formed. The total pressure acting inside the large soap bubble will be P prime equal Pa plus Pe. Therefore, P prime is equal P plus 4S by R. As the temperature remains constant, we can use Boyle's law. It will follow Boyle's law. And in this case, product of pressure and volume remains constant. Therefore, P prime V prime equal P1 V1 plus P2 V2. Or comma P plus 4S by R V prime equal P plus 4S by R1 V1 plus P plus 4S by R2 V2, where V prime is the final volume of the large soap bubble. Now, if we simplify, then P bracket open V prime minus V1 plus V2 plus 4S is taken common, V prime by R minus under bracket V1 by R1 plus V2 by R2, where V1 and V2 are the initial volume of the two small soap bubbles and V prime is the final volume of the large soap bubble. P bracket open V prime minus V1 plus V2 bracket closed 4S. Now putting the expression of V prime 1 by R dot 4 by 3 pi R cube minus under bracket 1 by R1. In place of V1 we can write 4 by 3 pi R1 cube plus 1 by R2 dot 4 by 3 pi R2 cube bracket closed equals 0. Or comma P bracket open V prime minus V1 plus V2 bracket closed plus 4S by 3 bracket 4 pi R square minus under bracket 4 pi R1 square plus 4 pi R2 square bracket closed equals 0. P V prime minus V1 plus V2 4S by 3 bracket open A prime minus E1 plus A2 bracket close into 0. It should be A prime, where A prime is the final area of the large soap bubble. Now V prime minus V1 plus V2 is equal to V, which is the consequent change in volume when two soap bubbles coalesce to form a large soap bubble, which is the consequent change in volume. Now 2 under bracket A prime minus A1 plus A2 bracket closed is equal A, which is the change in area or decrease in area when two soap bubbles coalesce to form a large soap bubble. When two soap bubbles coalesce to form a large soap bubble. Therefore, A prime minus under bracket A1 plus A2 is equal A by 2. The factor 2 is due to, now we get V prime minus V1 plus V2 as V, which is change in volume. A prime minus A1 plus A2 is equal A by 2, and the factor 2 is due to two free surfaces of each soap bubble. Putting these expressions in equation 1, these expressions in equation 1, we get PV plus 4s by 3 into A by 2 equals 0, or 3 PV equal 2s dot A. So therefore 3 PV plus 2 sigma A equals 0. Hence proved. 3 PV plus 2 sigma A equals 0. Hence proved. This is the required equation where S equals sigma, which is the surface tension of soap solution. S is equal sigma, which is the surface tension of soap solution. Here A1 and A2 are the initial areas of two soap bubbles, and if they coalesce to form a large soap bubble, in this case change in volume delta V will be V prime minus V1 plus V2, and change in area will be 2 under bracket A prime minus A1 plus A2. Now delta V can be denoted by V and delta A can be denoted by A, and we get 3 PV plus 2 sigma A equals 0.